One. All right, welcome everyone to this week's Zoom for Thought. This week we're going to have JJ tell us about toric varieties. Take it away.
Okay. So well, first I'm going to take a nice cool sip of water. All right. There's your shameless plug advertisement for water. All right. Now let me remind you of the setting. So you have spent X amount of years learning all of the abstract formalisms of algebraic geometry. But you don't know many examples. Especially concrete examples. Are we doing geometry or are we just doing algebra? Or maybe you don't know any concrete examples. That's sort of been me at various times, I think. And okay, so this is one situation that you can be in, or another situation that you might be in is you don't want to spend X years learning all of the abstract formalisms of algebraic geometry, all of the Grothendieck and Serres and all that stuff, but you want to see some interesting examples. Okay, so how do you come up with these interesting examples in a pretty concrete way? And the answer is combinatorics, my dear. I know there were a lot of people who were hoping for this. So let's talk about the combinatorics of some cones. Okay, so first of all, what is a cone? So let V be a set of vectors in Rn. So give me some set of vectors, V1, V2, all the way to Vr. But, well, that looks like VV. Let's make it VVR. Okay, we're going to be in Rn. So if it's 2 or 3 vectors, you can write it down. And so let's talk about the so we can have a cone, and we can make a cone out of these vectors, and so we'll define the polyhedral cone. I think polyhedral is like from the fact that we're going to make a sort of, our cone is going to have, you know, sharp edges rather than being like a round cone. So our polyhedral cone is just the set of all X such that X is a linear combination plus lambda R VR. So just the linear combination, and the linear combination, this is important, it has to be positive. So it's not a subspace, it's nothing like that. We're definitely not closed under addition, but we are closed under positive addition and scalar multiplication. So a nice 2-dimensional example here is this cone. So my 2 vectors are this guy, and this is just an example of a cone that they generate. Okay. It's fun I don't know, I found learning about cones to just kind of be fun, because I feel like this is something I could have learned in undergrad, but I never did. And when you think about what a cone is, you have a picture in your head, and this is more or less that picture mathematically. Okay, so for the cones we consider today, we want them to have a couple of characteristics. So number one characteristic we're going to want out of our cones is we want them to be rational. And what that means is that all of these VI basically just have integral coefficients in a standard basis. And that's equivalent to having rational coefficients in the standard basis, because the same cone is generated by scaling one of these vectors up or down, because we have we can have any coefficient in R here. So it's equivalent to each VI has rational coefficients in our basis. That's why it's called rational. But the other thing we're going to want our cones to be is convex. Okay. Convex is just your same old as you would see it probably in a lot of other places, where you have 2 points and you want, if you have 2 points in your set, you want the entire line between them to also be in the set. So this is a convex cone. If I had this guy and this guy, and I was looking at all of this stuff, that would not be a convex cone. We want our cones to be convex. I put it here because convex isn't, I know this is like super fundamental to some parts of math, but it's not something that comes up as much in algebraic geometry. So
wait, to clarify,
so the cones,
are there examples of cones that aren't convex? Okay. The audience seems to think no. The audience thinks all cones are convex.
Because you just get more positive coefficients.
yeah, I actually, you might be right.
I mean, it's fine to emphasize it.
Yeah,
So,
yeah.
we do like to have them convex. They just happen to be convex.
There's a notion of strongly convex, which means that you don't contain a straight line. Sometimes we'll want that, sometimes we won't. But yeah, I guess they are always going to be convex, aren't they? Yeah. There's also another type of object that you can look up called a fan, which is made up of cones, which is not necessarily convex.
Yeah.
So,
okay, cool.
But the convexity thing won't have, I mean, it won't have any real consequences for us. But it does, I think, give you a picture of what we're trying to do. Okay. So let's do some examples. I have 4 examples that I want to sort of walk us through with the whole way. And so what we're going to do is we're going to take these 4 examples. So what toric varieties do is toric varieties take cones and they associate algebraic varieties to them. That's where we're going. And so we're going to go through this whole process, and we're going to take 4 cones with us. And so these are the cones. The first one is the 0 cone. So the 0 cone, the set of vectors that we looked for is the set 0. It's pretty boring, but not as boring as the boring cone, which will be the set of E1 and E2, where E1 and E2 are our bases. And so the 0 cone looks from its cone picture like it's more boring than the boring cone. But don't be fooled. The zero cone is actually kind of interesting, and the boring cone is a lot less interesting. And we'll see this as we sort of go through the process. So the next thing, example number 3, is the quadric cone. So the quadric cone is generated by the vectors 2 times e1 minus e2 and just e2. So it's our first example of a very much a non-trivial cone, and this is one of the fundamental examples in algebraic geometry. And I'll save. We'll see it later. And then I wanted to give an example of a cone in 3 dimensions for us. So I've done this square pyramid cone that's sort of badly drawn right here. So you can sort of see me trying to put the square here. And so my vectors are supposed to be, let me write them down here. So it's going to be a set of 2 times e1. So I'm going to the x, and then plus or minus e2 plus or minus e3. So what does that mean? That means, so I'm going up and over 1, and then this way was 2, or I'm going over 2, up and towards 1, or over, up, and away 1, you know. So I have this square that's sort of centered about the x-axis, and then that square is 2 units away from 0, and I'm just taking the vertices of that square and using those to generate my cone. So this sort of, the idea of using a square here to generate this is going to kind of be important later. Well, it's important for toric varieties. We won't so much use it later in this talk, but the idea of having polygons in R3 sort of, or honestly in Rn, which I guess would be polytopes, to have polytopes to sort of generate these cones actually ends up becoming quite useful. Okay. Are there any questions about any of these examples? We're going to come back to them a lot. So if there are any questions. Okay. Let's talk about the dual cone. Okay. So we want to consider the cone on the dual space. So that's defined as so sigma is my letter for what a cone is going to be. Given a cone sigma dual is all of the maybe you could call them covectors in the dual space of Rn, such that, you know, when you apply them to the original vector, it's greater than 0. And so because we're in a finite dimensional space, this sort of dual pairing is really just the dot product. So what you should be thinking of is it's all the vectors u, also be, and because Rn dual is isomorphic just to Rn, again finite dimensional, the dot product, it's the things which dot product with the other thing to be greater than 0. And so we can actually calculate this dual cone in a very concrete way. And that concrete way is we take, well, basically we use what we learned in Calc 3. where, you know, the dot product is like the, you know, it's the norm of u times the norm of v times the cosine of the angle between them, something like that. So in particular, if the cosine of the angle between them is less than 90, then it's going to be positive. So in particular, we're looking for things that are in, say they're in with the cone, that for anything in the cone, it's going to sort of be within a 90-degree angle of those. And so what you can do to calculate it is you can sort of take the edges of the cone, and you know, you can look at so I have the quadrant cone here, so you can look at the edge here, and so you can write down all of the things that will dot with it to be greater than or equal to 0, which is this half plane. Okay, so this is my example here. Just have this half plane of things that dot with this guy. And then I can sort of, so certainly if something is going to be in the dual cone, it has to be dotted greater than or equal to 0 when it's hit this guy. But if I choose like some other guy in here to be dotted greater than 0 with this point right here, well, what that means is it needs to be on this half, right? It needs to be like less than 90 degrees away from this plane right here. So I would have to intersect this half plane with this half plane. So I get something like, you know, something like, yeah. I had this half plane, I had this half plane, so I get something like this. And I could keep going, and I could just, honestly, I could go to the other edge because I have to be dotted sort of close enough to everything that's in between here. I can just take the intersection sort of at both of the edges of this cone. So what I'll do is I'll take sort of the guys that will dot with this one and the guys that will dot well with this one. So I got this half plane and I got this half plane, and the intersection of them is this right there, which ends up being this. And that's the dual cone. And you can try to picture this in 3 dimensions, and it will be or it'll be a little bit harder. Are there any questions about how I constructed that dual cone? I sort of really explained it in words. So you can write it down more formally, but I just wanted to give you like the picture of it. Are there any questions about that?
So this is just the intersection of kind of like the half planes associated with the vectors that generate the cone?
Pretty much, yeah. Yeah, that's exactly what it turns out to be. That's not its technically what its definition is, but it's an easy exercise to show that yes, that's exactly what it is.
Well, that's why I'm a little bit confused about that, because I mean, if you are in the intersection of all the half planes generated by the vectors, then the inner product with amongst each of the vectors is going to be positive, and you're going to so then sure, your inner product with any of like with everything's going to be positive, but I'm guessing if you like expand the inner product using linearity, depending on if a certain v that you're considering. Oh wait, never mind. I understand. You're looking at all v's. Never mind.
Yes, I have to be dotted greater than or equal to 0 for all of the v's at once. Yeah.
Okay, that makes a lot of sense.
Yeah. And it's sort of a pictorial thing. You can sort of see it happening, where it's like if you got an obtuse angle and if you got an acute angle, the acute turns into the obtuse, and when you do this dual cone construction.
Right.
So let me do some more examples. So the zero cone is so right here I've got well, at least for the first three, my dual cones are in orange. So my zero cone here, well, anything dotted with 0 is 0, and 0 happens to be greater than or equal to 0. So it turns out all of R2 in this case, or Rn or whatever, is indeed part of the dual cone of the zero cone. Dual cone of the zero cone is the whole thing. And so that's as opposed to the boring cone, which if we intersect these half planes here, what we get is exactly the same cone. So this is part of the reason why the boring cone is boring. But you can, what I was saying sort of about how, here's the quadricone, here's the example that we just did. The sort of acute angle in the dual cone turns into, or the acute angle in, or I guess it's an obtuse angle in the original cone turns into a sort of an acute angle in this dual cone. And if, of course, if this were the original cone, its dual cone would be the other one. The dual is a reflexive operation. Again, we're in finite dimensions. It'll just work. So you have this sort of duality sort of with acuteness and obtuseness. Well, at least in 2 dimensions, I guess in more dimensions than 2, I don't know if I know exactly what it means to be acute or obtuse. Maybe someone has a definition somewhere, but you can sort of see this sort of tight in versus spread out sort of duality going on. And this 90-degree angle right here in the boring cone is exactly the fixed point of that. So maybe that's sort of our intuition as to why the boring cone is boring. And then the square pyramid cone, because I made it go out 2 in the x, it's sort of scrunched up here. So when you take the dual cone, you get sort of a, so first of all, you get the faces sort of switch sides with the edges of the cone. And the second thing you get is that so the edges are now like on the coordinate planes. So, and then because it was sort of scrunched up here, it becomes sort of more spread out. So I think of this sort of like a, so this is sort of like, I don't, my drawing might not be very good here, but it's sort of like a sort of diamond shape. If you were looking straight at it, it would be like this sort of square diamond kind of shape there. Any last questions about the dual cone? Yeah, Sam?
Yeah, so you may not know the answer to this, but like if you in general take one of these constructions generated by like a polytope and you take the dual cone, do you get like, there's this notion of like a dual polytope. Is this dual cone now generated by the dual polytope?
I would expect that to be true. I don't know enough about polytopes to tell you.
Yeah, fair enough. Neither do
I. But I would buy that. Any other questions?
In the square pyramid case with the diamond, the square sort of like before you do the dual operation, that like, is that inscribed into the diamond, and that's how you're that's what you end up getting?
I don't know if this is a general thing, But it is true that in this case, if I take this square and I mean, if I were to draw it on top of each other, it would be like, right? Like, how do I say this? Like this guy right here.
Could you?
I mean, okay.
Could you
I guess
draw
if I take this square, so the place where this diamond sort of stops is 1 unit out, and the place where this guy stops is 2 units out. And so if I take this square and I push it 1 unit there, it will be inscribed in the diamond. But I don't know if that's like a sort of general phenomenon thing.
Oh, okay, I see. Thanks.
It's yeah. I don't know, but it's some kind of interesting geometry that you can really picture, which is part of what I like. Okay. Okay, so now let's talk about monoids. So from the dual cone, we're going to take a monoid. And what's this monoid going to be? Well, so I defined a lattice that was Zn. Inside of Rn, I can take the dual lattice of that lattice, which will again be isomorphic to Zn. I'm going to call that M. This is just the standard name you call for this dual lattice. It's just M. And then what you can see is that if I take this dual cone and I intersect it with the lattice, sigma dual intersect M is an additive submonoid of this additive group, but it's not an additive subgroup. There's no inverses. It's just an additive submonoid. But I get a monoid. It has 0 in it. That's the identity. And because it's a cone, that gives us that it's closed under addition, and everything else sort of 0 is the identity. Everything else just sort of follows. So this monoid we call S sigma. Okay, so let's talk about the monoids of each of these guys. So the first one, the 0 cone, S sigma, is actually just M, right? Because the dual cone was just R. And in this case, it's Z, well, it's Z to the N or Z2. It's isomorphic, I guess. So we have this, I write it down as a lattice right here. So you can see that. The boring cone, you just intersect. You just intersect it with Z2 again. Same with this quadric cone. Now it's kind of interesting. We've got some sort of pattern going on. And then what you'll do with the square pyramid is I haven't drawn a lot of it, but you can see that there's this sort of diamond shaped kind of grid of lattice points, and these and the linear combinations of them, the positive linear combinations, or I guess integral combinations, will generate that monoid. Any questions about our monoids? Okay. So now we're going to come to the most important step in our construction, which is also in a way kind of the hardest step, which is we're going to find generators and relations for all of these monoids. So okay, let's do this. We need to find the generators and relations for all of these monoids as monoids. So that's important because this is an additive monoid. So the zero cone, it's not just generated. So it's not just generated by E1 and E2, of course. These are linearly independent. But you also need to throw in, you can only take positive linear combinations. So you need to throw in minus E1 and minus E2. Minus E1 and minus E2. Whoops, minus E2. Because it's a monoid. It's not a group. You want to think about it as a monoid. And so I can write that down abstractly as this. I can write it down as A, B, C, D, subject to the relations A times C equals 1. And B times D equals 1. Okay, so I took a jump here, and that jump was from additive to multiplicative notation. So I want to switch to multiplicative notation. So the whole point of this construction was to get me some good way of having these relations right here. Those yummy relations are sort of what I'm after.
Should we just implicitly assume that in all of your presentations, we should also add the commutators so that it's a commutative monoid?
Yes, everything is commutative.
Okay, cool.
Already.
Cool. Definitely don't bother writing it, but I just wanted to check that it's always implicitly assumed you're commutative.
Yeah, so this, okay, so I'm using this notation like it's a quotient of a free group. It's really not. I guess maybe it's a quotient of a free commutative monoid. But this, for me, this is really just a notation. Sort of make that clear for the purposes of this talk. So yes, everything is commutative. Okay. So if we talk about the boring cone, we only have this quarter of the plane right here. There are no generators and relations. No gens or relates. Another reason why the boring cone is boring, I have none of those really good relations that I was after. Okay, let's move on. That was boring.
Sorry, what do you mean there's no generators?
Well, that's not true, is it? There's no relations. There are two generators. Sorry about that. I guess it's a little of a typo.
There's no generator relations.
There's no relations between the generators. There are generators. That's true. So you talk about the quadrant cone. That's generated by E1 plus E2, and 2E1 plus E2. So if you look at that, you can sort of see it visually. So zeros here, I can use E1 and I can get to a lot of things, and I can use E2, but to get all of the things, I need to use this vector 2 in order to generate the thing as a monoid. And once I have this vector, I can get anywhere I want because I can sort of get to any vector as high as I want. And then once I'm as high as I want, I can go to the left with this E1 right there. There's also a relation. It's a particularly interesting one. So that relation is E1 plus 2E2 equals 2 times E1 plus E2. And so you can see that visually too. This is E1 plus E2. So if I go that twice, that gives me the same as going this just E1 once, and then 2E1 plus E2, or 2E2 plus E1, I guess. It's really 2E2 plus E1. 2 E2 plus E1. So that is, that's that. And I can write this one as generated by A, B, and C, such that B squared equals AC. Okay. And now the square pyramid. Rather than taking 2 hours and doing the square pyramid out by hand, I did it beforehand. And it looks like this. These are the generators and relations. There's 13 of these points that you'll need to generate the lattice. And I plugged into a computer, and these are all of the relations that you'll need. So for example, x1, x2 equals x4 times x11. I believe x1 corresponds to this middle point right there. But the point is, I guess, that this computation basically turns into linear algebra over Z. It's not too horrible. And so finally, our last step, we can say we've constructed algebraic varieties, is to take the zero sets of the relations. So this is why I wanted to think of them multiplicatively, because if I think them multiplicatively, they are polynomials. So to take to remind you what I did with the zero cone is A, B, C, and D. So I want to look at A, B, C, and D in C4 such that AC equals 1 and BD also equals 1. So those were the two relations that I got over here. And so what set is this? Well, if you're talking about if you're talking about this restriction right here as a polynomial, what that's going to mean is that A is equal to 1 over C, or A is equal to C inverse. And also B is equal to D inverse. And those are the only two restrictions you have. So what you're getting here is a copy of the units and C squared. You're getting two of them because you have two copies here. So this is called an algebraic torus. It actually contains a usual torus, a product of S1s. You can see that because C cross is the same thing as S1 cross R greater than 0, greater than or equal to 0, I guess. But so this C cross, or a power of it, is what's called an algebraic torus. And this is where toric varieties get their name. This is sort of the most basic one of them. And it plays a fundamental role in the theory when you go further. Any questions about the algebraic torus that we got from the zero cone? Really quick.
I think maybe you should take just the positive real numbers. Right? I'm a bit confused by that.
Yeah, I don't want to include 0, do I? Like this?
Yeah, that's what I think.
Yeah, that's a little typo there.
I just had a
Okay.
general question.
Yep.
So why did we move to the dual in the first place? Like, can't we just look at the relations just in the actual cone?
Yeah, yes. So the answer is we want our the real answer is we want our construction to be sufficiently functorial. So we want, if I include my cone into another cone, then the toric variety that I get, which is, for example, like the algebraic torus, is included into the cone that we started with. So like if I have a cone that's inside another cone, right? So if I have a tau inside sigma, I want x tau to be inside x sigma. And so what happens is when I take the 0 set, that is contravariant. It would be, if tau is in sigma, it would be that x sigma is in x tau, and it's just harder to think about. So I think people chose to use that. I think that's why people chose to do the dual cone construction in the first place. I don't know. Does that help to answer the question?
Oh yeah, that answers the question.
Okay. So maybe for our boring cone here, the x sigma is going to be, so x sigma, I guess x sigma is just a name for the toric variety. So this is a toric variety because we made it with this construction. There were no relations. There's nothing to take the 0 set of. We just get C2. And that's boring. So for example, although I don't know, it's nice to just have C2 and see that we can recover the whole, complex 2 space with this construction. Okay, and so the next one, the quadric cone, is a set of A, B, and C in C2 such that B squared equals AC. So if I'm drawing X sigma, the way that I would draw it is like this. If you think about it, if you think about this equation in real 3 space, that's what it will be. We're thinking about it in complex space, but you can see this sort of as the sort of quote unquote one that I can draw a picture of, because complex 2 space is 4-dimensional, so I can't exactly draw it. But so I'll draw this instead. But this cone right here, and this is sort of the same cone that you talked about conic sections with. If you talked about conic sections, maybe when you're in one of your first algebra classes. And so the interesting thing about this is that it's not a complex manifold. Right here at 0, it's not smooth. And you can show that, and as Thomas said in the comments, you can detect whether a toric variety is smooth or not, using properties, using combinatorial properties of this cone that I don't really have time to talk about. So last but not least, we just have our square pyramid, which is a 3-dimensional. We just have all the relations from before. And there ends up being 10 of them. If you count, there are actually 10 of these. So the shape that it cuts out is actually 3-dimensional. And it's inside of C13. So yeah, a little bit of an addendum there. So that's most of what that's most all of, actually that's what I wanted to get through for this talk. So are there any questions? So I just
First, let us thank the speaker. All right, go ahead, peeps. Ask your questions.
Yeah, so 2 questions regarding this slide. So first of all, the square pyramid, does this 3-dimensional thing look nice? And, or I mean, offhand, do you know what it is, and does it look nice?
So it's 3-dimensional in the sense that it's locally 3-dimensional. I don't know what it looks like because it lives in 13 dimensions.
Sure, I guess my question was, do you know if there's like some nice embedding of it into, like, you know, roughly 3 dimensions? Or
yeah, I don't.
Yeah, that's fine.
I assume there's a lot of symmetry in that in that sort of diagram that we saw. So I would believe it if it could be embedded into something much smaller. Unfortunately, I was going to try and use some computer programs to get like a pretty picture of like a toric variety that lives in C3, or maybe print the real part of it. But I think I don't know if the software to do that exists. So
Yeah.
so I was able to get the computer to spit out all of these relations for me. So I at least those.
And the second question I had is, so you mentioned that, you know, if your cone 1 contains cone 2, then this variety will contain the other variety, right?
Yes.
So does that mean there's a copy of like C2 in the quadric cone? And if so, where is it?
So there's not, so okay, so I said contains, and I was being a little bit imprecise. Really, if you think about it, if I take one of the faces of these cones, that itself is a cone of dimension 1 less, sitting inside the same ambient space. And that cone that's dimension 1 less is the thing that you can include. So you can put an order on the edges and the faces and include that. So in particular, what this does say is that in every toric variety, there is an algebraic torus.
I see.
And because of the way things work in algebraic geometry, this algebraic torus coming from the 0 cone is actually a dense subset, which is kind of interesting. So every toric variety has some algebraic torus as a dense subset. So yeah, so it doesn't necessarily have a copy of C2, at least not coming from this, but it does have a copy of, say, C1 coming from just the vector E2, just one of the vectors.
Yeah, cool.
And has a copy of an algebraic torus. Yeah.
Thank you.
Any other questions or comments?
Yeah, so it seems like there's maybe like multiple ways to like present these monoids, you know, just with different generators relations. And so is it going to happen that like you get the same like varieties coming out of these different presentations?
It should, yes. So one of the things that I didn't go through is that you can actually make this slightly more formal. Rather than just finding generators and relations, you can actually construct a ring, which like sort of has the generators and relations. So with a ring, when you have the two different, I mean, it'll be the same ring. The ring is there kind of regardless. So if you have two different sort of presentations of it, it'll end up being the same, just because that's how just because they're going to be isomorphic rings.
Yeah, so it's just something like K adjoin, like, you know, X, Y, Z, whatever, mod out by these like ideals.
Yeah, it's K adjoin all of these guys. Oh, I think my pen's run out of battery, but it's K adjoin ABCD mod out by AC equals 1 and BD equals 1 for S sigma there. So if you know what localizations are, you see that this is the same thing as localizing those localizing two guys there, which sort of shows you why you get, which shows you algebraically why you get the units.
Cool.
Anyone else?
I have a question about, so, you know, when you were introducing the dual cone, could you go back to that part? Yeah. And it's like all the half planes, etc. The actual dual cone, like from this construction, it looks like everything that's in the dual cone. If you, let's say you take all like the vectors that generate the cone, right? And you put them into a matrix, everything that's in the dual cone are exactly those vectors. When you apply, let's say the matrix is W, then you apply W transpose to it. That those should all be in the positive orthant, right? Like so is there some type of like, oh, sorry.
Like equivalently, like exactly what you're saying is take each orthogonal complement and the positive side of that with respect to that the generating vector, and intersect all of those positive parts of the orthogonal complements. That's like exactly the same as what you said. So that's good.
Yeah. And I guess like I'm also like curious about if this like dual cone is the one that goes to the positive orthant, then what are the, like, I don't know this. I was wondering if like you've thought about it, or if anyone's heard about this. Like, are all the vectors that end up on, like, I don't know, like the 1 1 like a certain other orthant, are those also defined as like a cone that are generated somehow from like maybe a subset of these vectors or something? I don't know if anyone's ever thought about that.
I think, I don't know, but I think the answer is if you took another orthant, you could replace one of the vectors in your matrix with one that's sort of orthogonal to it, and then it would be in the positive orthant, right? I'm pretty sure you could just do that.
Yeah.
So I'm pretty sure this would be the dual cone of a different cone that you could find by some sort of transposition or translation.
That makes sense.
Transposition and translation are not the right words, but
I see what you mean though.
yeah.
So is the variety that you get from this always irreducible, or is that too much to hope for?
Don't know off the top of my head. I don't know off the top of my head. It might be. There's properties of the cone that can detect whether the variety is proper or projective or something like that. I only did the affine case here, but Yeah, I'm not sure. All of these examples I think are irreducible.
Sweet. Anything else, anyone?
Yeah, I had a question. So if you're given a variety, how do you know if it's a toric variety or not? Like without this cone construction, is there like an equivalent way of checking that?
There might be. There's a very necessary condition. So the very necessary condition is that it contains an algebraic torus as an open-dense subset, which is actually a pretty strong thing. It means that, so I'll use a few words here, but it means that you're birational to projective space, which means that most of your variety can be covered by the complex numbers. So the word for this in algebraic geometry is rational. It means that your variety is rational. All toric varieties are rational. Now, I'm pretty sure there are rational varieties that are not toric. Otherwise, we would just call them toric varieties and we wouldn't have the word rational. And I don't know how to tell those apart. Maybe there's a way, but
Proof by terminology.
so for example, yeah, there is no way your elliptic curve or your surface of genus 2 will ever be toric. The cool thing about toric varieties is they can give you examples that are singular, and you can sort of cook up things like this quadric cone, which are example of sort of interesting singularities.
All right. Anything else? Fantastic. Let us thank the speaker once again.